Hola.
Hola, hola.
¿Cómo que no sé?
Buenos días.
Hola, buenos días.
Hola, hola. Em,
¿Qué?
¿Qué trae puesto, gallo?
¿Cómo?
¿Qué trae puesto? ¿Es un saco?
No, es una sudadera.
Ah, ah.
Sí tengo sacos, pero no. No me los pongo.
De la perspectiva parecía un saco. Dije, hola, la.
No, todavía no.
Está bien.
Creo que ahí está. Se me rompieron mis lentes, por eso.
Chale.
Bueno. Ah, ya sé, Jero, te voy a pasar para que seas ¿cómo se llama? Co-anfitrión. Jero. Por. Jero. Por. Sí. Y también déjale, comparto. Y ya todos pueden compartir pantalla. Igual, Alexandra.
Sí. ¿Qué onda? Saludos a todos. Ahorita me...
Hola, hola. Oye, Gallo,
Buenos
yo
días.
estoy también como anfitrión.
¿Cómo?
Estoy también como anfitrión, es que me aparece a veces el letrerito de si puedo admitir o no.
A ver, fíjate, sí, eres anfitrión, te acabo de poner.
Ok, ok, gracias.
Entonces tú puedes admitir a la gente que quieras. Ay,
Hi.
Hello. Um, Hi. We're just gonna wait a couple of minutes to more
Yeah,
people.
just a
join.
second. I also will switch on my second device because I want to share the screen. So.
All right.
ok.
Okay. You can see my screen, right?
Yes.
Yep.
We can start whenever you wish.
I'm ready. So if you think that it's a good moment, we
What-
can
what-
start.
What do you
Yeah,
think, Hero?
Yeah, I think we're 15. Yeah, we're 15 people. So I think we can start. Let me just introduce you and present the seminar. Well, first of all, welcome back. Well, at least the first sentence will be in Spanish, and then I'll switch back to English. So, bienvenidos todos al seminario Tartaglia en este nuevo semestre que reiniciamos. Y hoy nos va a acompañar Alexandra Skripchenko. Entonces ahora voy a cambiar inglés para que nuestra presentadora nos pueda entender. Now, welcome back to the seminar. Let me introduce our speaker, Alexandra Skripchenko. She is currently an assistant professor at the Higher School of Economics in Moscow, Russia. She is also a senior research assistant at Skoltech. Alexandra's research, which has been published in prestigious journals like Ergodic Theory and Dynamical Systems and Invenciones Matematicae, among others, focuses on ergodic theory, symbolic dynamics, geometric group theory, and low-dimensional topology. Today, Alexandra will tell us about a family of interval translation mappings in Hartog double rotations and their ergodic properties. So please welcome Alexandra, and please start. Thank you for coming.
Thank you very much for the invitation. I'm very happy to extend my geography. I'm very curious to visit Mexico at some point in a real way. Many of my friends are now in Mexico because they enjoy their vacations there. So I feel not such a loser, because I also can tell them that indeed I visited Mexico as well, even just for 1 hour. And I'm going to tell you indeed about quite a new and simple plot that attracted me and several of my colleagues who were typically working in Teichmüller dynamics and dynamics of billiards. I try to stay very elementary, feel free to interrupt me at any moment. So before I introduce you my real protagonist, who is a double rotation, let me tell you about more famous relatives that double rotations have. They are named interval exchange transformations. You know, in every family, it's a rather typical situation when there are some people who are famous and successful and so on, and everybody knows them, and there are always many poor relatives that are much less famous and successful. So the same thing happened to this family of maps of intervals, because EETs became real star, and they attracted plenty of gorgeous mathematicians and forced them to study them. But other people who are very similar with interval exchange transformations did not get such a glory. So as a kind of a teaser and advertisement for today's talk, let me start from the most famous person, even if I'm not going to prove anything new about this guy. So the definition is very simple. We take an interval of a real axis and we divide it into parts. And then we consider a map from the interval to itself, such that this map is simply a translation on every interval of continuity. So, for example, this triangle guy goes here to the triangle part. Maybe I should use more colors to make it more explicit. So this guy moves here. Then these guys, they move here. And then I keep it black or maybe blue. This person is, just a second. So he will be blue. And this guy will go here. And the idea is that we have a piecewise continuous map, which is a rotation preserving isometry, so simply a translation on each interval of continuity, and it's organized in a way that when we collect all the images, we get a partition of the original interval again. So why do people care about such a map? The first famous motivation comes from the study of dynamics of billiards in rational polygons. By rational, I mean that the angles of the corresponding polygon are always given by a rational number multiplied by pi. So for example, a classical billiards that you play in a rectangle is a good example of such a map. Or if you prefer to make your life complicated, you may play a billiard, for instance, in hexagon or in some very complicated polygon. And the only things that you require is that you have P and Q natural numbers, right? So in this case, the polygon is called rational. So what is typical billiard is that you consider a trip of a ball with a unit speed, such that once you touch the border, you respect the law of geometric optics. So it reflects with the same angle as the angle of arrival. And then you ask yourself what's going on with the typical trajectory. Either you have a periodic trajectories or not. And if you don't have periodic trajectories, maybe your typical trajectory is everywhere dense or not, and these kind of things. So people started to study this subject quite a long time ago. And very easily they discovered that apparently the first return map to the transversal for a rational polygon, for the billiard in rational polygon, is exactly the interval exchange transformation. So the first return map. Oops, I apologize. The first return map on the transversal is given by interval exchange transformation. So instead of thinking about such a complicated geometric object as billiard can be, you may force yourself to think about something very simple and pretty combinatorial in its definition. Another source of motivation comes from the study of measured foliations on surfaces. So once again, imagine that you live in a very orientable world. So your surface is orientable. And for example, the foliation is defined by one form. So it has some singularities plus surface. And the surface is oriented. And you would like to know something about the topology and geometry of your leaves, if they are everywhere dense, if they visit with the same probability any part of your surface, or they accumulate in some small part of the surface, or what's going on. And once again, the first return map to the transversal is given by interval exchange transformation. So it's just two examples. In reality, one can find much more to convince him or herself that it's cool to study interval exchange transformations. But what I want you to understand is simply that such a simple object can be used to understand much more complicated dynamical systems. So what do we need to know when we have an interval exchange transformation? What do we need to know to define it? We need to know two things. First, we want to know the length of the intervals. So I would like to understand what is the length of the blue, red, and the green guy. And also I need to know in which order do they appear on the top level and on the bottom level. And the second part can be definitely coded by substitution or a permutation even, it would be simpler. So you can think that you have a permutation, and this permutation is responsible for the order in which your intervals appear on the top and on the bottom level. And so that's enough to fix the whole picture. And very often mathematicians like to think about interval exchange as about a normalized thing. So they fix the length of the whole interval and say that it's equal, for example, to 1. So in such a case, it's enough to know all the other lengths. And so you live in a simplex and projective space. And once people understood that they can replace the study of these complicated dynamical systems by the study of interval exchange transformations, they stated a few questions about these objects. The first question is either it has a periodic orbit or not. Then if you don't have a periodic object, is it true that you have a everywhere dense object and the orbits? So, and if it's true that they are distributed in a kind of equal way. So you would like to understand if the minimality holds. By minimality, I mean that all orbits are everywhere dense, or maybe you have just topological transitivity when there exists just one minimal or everywhere dense orbit, and not all of them are like that. And then the next question is, what about the invariant measures? Obviously, the Lebesgue measure that lives at the interval is the invariant measure for such a map. So you ask yourself if you have other measures that are invariant, and if it's ergodic measure, and if it is an ergodic measure, is it true that all other ergodic measures are equivalent to this one? So you would like to understand what about the ergodicity and unique ergodicity of the invariant measure. And if you get all these things, then naturally you can increase your level of interest, and you can also ask yourself, what about, goodness, today it's very inaccurate, weak mixing and strong mixing, and so on. So all these questions were posed. And before I tell you the answers, let me comment a little bit at the history. As most part of Russians, I'm very interested in the history of mathematics, partly because we had many great mathematicians and all of them were very serious about their own contribution. So it was very important always when you're a young student and you give a talk, not to mess up in this historical part. So the history of interval exchange transformations is rather complicated because the object looks so natural that too many people discovered it simultaneously. But it seems that the general definition for the first time was given in a paper by Valery Isometries, the person who proved multiplicative ergodic theorem. At that time, he was still a student of Yakov Sinai. But this definition generalized an object that was already introduced in a paper by Vladimir Arnaud. And Arnaud's motivation came from the following fact. Actually, if you consider an interval exchange transformation of two intervals, and you switch to the circle instead of work with the interval, so you glue 2 points, the ends of the intervals, and you come to the circle, then your map is nothing else as a rotation of the circle. So what Arnaud did, he tried to generalize the rotation on the circle and considered an interval exchange transformation on 3 intervals. And then Isometries defined it in a full generality. But in reality, many other strong people arrived to the same idea more or less simultaneously. So Bill Thurston already knew what interval exchange transformation is because he worked a lot with foliations. And at the same time, Anatol Katok and Anatoly Stepin, who were working with billiards, they also arrived to the same notion. So it's very hard to say who in reality introduced EATs. And the only thing we can say is that they were born in 60s in 20th century. And probably their homeland were the USSR. But many people could argue for the priority in this context. Anyway, once we have the object and we have the list of questions, I hope it's clear who the orbit is because you just have this map, and the map on each interval of continuity looks like something like that, where gamma eta is chosen in a way that all these images agree with each other. So I hope you understand who is the orbit, and then it's time to tell you something about the answers and the tools that were used to reach these answers. So the first theorem is due to Michael Keane, but before I state it, I need to comment on one pretty obvious but still important fact. So let me look at my interval exchange transformation. We agreed that I need to know the permutation in order to present it, to code it. So once we look at the permutations, there could be the following situation when the permutation splits into two parts and the life happens independently in these two halves. What do I mean? For example, the situation when we have a permutation like that, 1, 2, 3, 2, 1, 3. So if you draw a picture, what happens here is that you have 1, 2, 3. And then the third person is always on its place, and only the person number 1 and number 2, they switch with each other. Then it's quite obvious that if you consider an image of a point that started somewhere here, or on the interval number 1 or 2, you will never get into the second half given by the interval number 3. So if you know that your permutation splitted into two parts, you can be sure that it's impossible that your interval exchange transformation is minimal. So since we are interested in minimality, we exclude this situation. And we will say that if your permutation does not split into these two parts, it would be correct to say that this permutation is irreducible. Be accurate, because algebraic people, they mean much more complicated thing by irreducibility of permutation. And it's a punishment of the students of the first year to treat this question of irreducibility. Here, I simply mean that the permutation does not split into two independent parts. And so if we restrict ourselves to this irreducible case, then it's enough to require the following thing. So let's say that ET satisfies IDOC, or simply Keen's condition, if two singular points never meet at the same orbit. So what do I mean? Is that I consider the images, the singular points, they are the ends of the intervals. All these points, it doesn't matter on the top or on the bottom level. And so I take these points and I consider T of AI, T square of AI, T cube of AI, and so on. And all these points should be different. For example, it's true if we assume that all the lengths are rationally incommensurable. So example, it's not the necessary condition, but if you know that the lengths are rationally incommensurable, then it always will be true. They will not meet at the same orbit. So if you know this, if the Keen's condition is satisfied, then you can be sure that your interval exchange transformation is minimal. So in particular, it means that almost always interval exchange transformations are minimal. What do I mean by almost always? It's a precise mathematical term. It's not just a way to say it in a beautiful manner, because you can put a Lebesgue measure in the simplex that is associated with length. And so bad things happen only when this condition is violated. So when you have rational commensurability between some lengths. Of course, these subsets, they form a zero measure subset in the set of the whole parameter space. So almost always, if the permutation is irreducible, almost always the corresponding interval exchange transformation is minimal. I will comment on a proof a little bit later when we will discuss the main tool that exists for such a case. But before, I would like to state more theorems that answer the questions that I advertised. So just one important remark, that this condition is sufficient, but it's not necessary. So it's not a criteria. It's important, and this gives us one of the most challenging open problems that we can state in this direction. Imagine that you have a family of interval exchange transformations for which, for some reasons, you know that there are some rational relationships between the length. For example, I don't know, the first length is equal to the last one. And then you would like to understand either most part of members of this family are minimal or not. Up to now, the precise answer is given only for rank 2 interval exchange transformations. Rank means the dimension on the cube of this set of lengths. And it was provided by Michael Bashar-Nitzan, a very brilliant mathematician who quite recently passed away. So this is a result for rank 2. He gave an algorithm how to understand if a particular EET that does not satisfy Kin's condition, in case if it has rank 2, if it's minimal or not. And there were some observations made by Ivan Dynnikov and myself for the possible conditions, or what kind of restrictions in a sense of rational relationships among the lengths we can have, and how do the structure of these relationships influence the minimality. But there is no full answer on this question. So if you are looking for ambitious project, welcome on board. It's very easy to state, but it's very hard to solve, it seems. Then in the same paper, it's a paper from, I think, 1975, when Kin published it. And in the same paper, he posed the question, either typical interval exchange transformation, which is minimal, is necessarily uniquely ergodic. And this conjecture was proved 7 years later in 1984 by Howie Mason and Bill Veach. They were working independently, and they found out 2 different proofs that were published in the same issue of Annals of Mathematics. So they published the proof of the following theorem, that almost all interval exchange transformations, we assume now that the permutation is irreducible, so almost all of them are uniquely ergodic. Unfortunately, the first important thing to understand is that there is no such a nice description as we had here of any sufficient condition, at least. So we don't have an obvious Diophantine conditions that would guarantee us that we live in a uniquely ergodic or non-uniquely ergodic case. Here, the estimation is done on the dimension of this set, but the description of the set is much less explicit. And the second point is that this theorem cannot be seriously improved, in a sense that between these 2 moments, people already constructed quite a few examples of non-uniquely ergodic interval exchange transformations. So those that admit more than one invariant measure. One was a Lebesgue measure, but there was another measure that was not absolutely continuous with respect to Lebesgue measure and still invariant with respect to interval exchange transformations. And so some famous examples are given by Keynes and Newton. And then Kin himself also provided some nice examples, and Veach contributed as well, exactly because he understood very well the connection between interval exchange transformations and the billiards. So this theorem could not be improved. And more or less at the same period, people asked the question, how many measures we can have? Measures. If we can have more than one, is there any smart limit? How many we can have? And then they started to think about more advanced properties like weak mixing, strong mixing, and so on. Some partial answers were obtained almost immediately by Katok. So what he was able to do is the following. He proved that the number of invariant measures, ergodic measures, okay, ergodic measures is bounded by the following things. So he defined it in terms of the number of intervals. You may not have more than the integer part of half of it, or half of it, or half of n plus 1. And the second, so he bounded this thing, and moreover, he was able to be quite precise. So this boundary is efficient, and it's a result of his student Evgeny Sataev. It's still from early 80s. It's more or less the same period when Mazur and Beach received their results. Recently, this result was improved by John Fickenshire, who constructed more generic examples, if you want, for any possible number of measures. And then, as for mixing part, it was treated by first Katok himself, who proved the absence of strong mixing. And for a very long time, there was an open conjecture if it's true that typical interval exchange transformation is weakly mixing. And the only proofs that existed corresponded to the case when you have 3 intervals. It was due to Katok and Stepin, but it was very specific to this small number of intervals. So in the most general condition, the statement about weak mixing was proved by Artur Avila and Giovanni Forni in 2007. Almost every ET except rotations. Sorry, I will extend the blackboard. Rotation. Is weakly mixing. It was one of the results that was mentioned by a Fields committee when Artur Avila got his Fields medal. So I think it's time to stop to mention the names and to kind of aggress you with the information. And maybe I should say a few words about the tools that was used to obtain all these results. Of course, some theorems, especially the theorem by Avila and Forni, they are very complicated, so I don't have time to provide you the full proof. But all these things use the same observation, that there exists a kind of a renormalization scheme for interval exchange transformation, and the scheme is named after Gérard Rosy, a very famous French mathematician. So the idea is the following: you start with some interval exchange transformation. Let me repeat the picture, maybe in a slightly different mode, but since I want to work always with irreducible cases, I'm supposed to not to vary too much the order of the intervals. Here is not a good example, actually, because I could join these 2 persons, but okay, it's not important. So anyway, I take this interval exchange transformation and I want to construct another one with a smaller support interval such that it would have the same behavior of orbit. So the orbits that used to be everywhere dense, they stay everywhere dense, and the orbits that were finite, they are finite, and so on. So the idea is the following: I have to consider the first return map on a smaller subinterval. And this subinterval is canonically defined. So if I use the induction from the right side, I need to find the longest subinterval whose left end coincides with the left end of my support interval, and whose rightmost end is the singularity, which is the rightmost one that does not coincide with the rightmost end of the support interval. So in my case, it's this person. And then I have to do the following thing, that I have to consider the first return map here. So let me check what's going on and what happens exactly. This long grounded interval, it just goes itself without any change, nothing happens to it. While to other people, they have more interest in life. In particular, let's see what happens with the triangle interval. It goes here under my map, but I don't care anymore about this part of interval because I only want to return to this green one. So where should I go? since I know that this part is identified with this part of a rectangle guy, I know that I then should take my subinterval here. So my triangle goes here. And then there is a small piece of the rectangle guy, and it goes immediately to itself. In other words, what can I say about it is that I should look at the rightmost end of my picture and see who is the longest interval, the one on the top or the one on the bottom. And apparently they cannot coincide, because either they are the same interval or the King's condition will not be satisfied. I prefer to live in a perfect world when King's condition is always satisfied. So they do not coincide. Then it means that one is the longer one and one is the smaller one, the shorter one. So if I, for example, have the situation as here, when the longer one lives upstairs and the shorter one lives downstairs, then what should I do? I should find a couple of this longer interval, and I will split my longer interval into two parts. One is the one that was glued to this guy on the bottom, and one is the remaining part. It's what's going on here. So this remaining part will preserve its position, and this guy will be replaced by a triangle. In the terminologies that people usually use when they discuss the inductions, they use the names of winner and loser. And apparently the terminology is quite strange, because they call the winner the longer guy, the one who loses his length but preserves his position. So we still keep its position. It did not move. It still leaves, keeps his number 3 at the top level, right? While the loser, it's not such a loser. It depends on your psychology if you can call it a loser, because it doesn't lose its length. It just has to move. It changes its position inside of the permutation. So that's what happens here. And this procedure can be described as usual by two things. One is responsible for the combinatorics. So you have a permutation P1, and now you go to a new permutation Pi2. And then the second thing is responsible for the length. So with length, the following thing happens, that all of them are preserved except one, and this one length is replaced by the difference between two, between the longest one and the shortest one, because this remaining part that preserved its position, its length is exactly given by this thing. So what do we mean is that we have some procedure that looks a little bit like the Euclid algorithm for continuous fractions. And at the same time, it contains a combinatorial part when you have a graph. It's called the Rossi diagram, with a finite number of vertices, because it's just the permutations of n elements, and even not of them happen. And so you move on this graph while you apply your induction. At every moment, you have this move at the graph, and you have this application of the algorithm that looks like a Euclid algorithm. And it allows you to construct the interval exchange transformation with the same ergodic properties as the original one. So what people did, they simply replaced the study of the ergodic properties of original interval exchange transformation by the study of ergodic properties of this mechanism, of this algorithm, which can be seen as a representative of a multidimensional continued fraction algorithm. So a Markovian one, moreover, quite simple. So it's quite exciting because it allows you to prove many things by a very low price if you want, because this algorithm is rather general. At the same time, it's true that you only can apply it to almost all interval exchange and not to all of them, because you need King's condition to be satisfied. In some sense, you can not see directly why it implies the unique ergodicity part, but I can comment on it relatively informally. Why do we think that it's true? Because if you write the matrices that would describe this procedure, And typically, you know, in ergodic theory, people write the matrices in a way that old lengths you should express in terms of new ones that are smaller or equal. Then you will have matrices with non-negative elements. And if you apply your algorithm for a long time, you will get matrices with strictly positive entries. But then you have a map in the set of parameters such that would be strongly non-expanding, but even a contracting one, because you have strictly positive entries. And so you can expect that your original cone where you live, the cone of length, will become smaller and smaller, and finally you get a ray instead of the whole cone. And what Witch realized is that there is a duality between the dimension of these subcones that you get after an infinite time of application of this procedure and the number of ergodic measures. And so if you have a ray, as I said, then you can be sure that your original thing was uniquely ergodic. So the way to prove the theorem by Mazur and Witch, one of the possible ways to think about it, is to notice that your map will be contracting due to the fact that the elements of the corresponding matrix become at the beginning non-negative and then they are strictly positive. So it's kind of an informal explanation. And another thing that I wanted to mention is that you can informally explain also using the Ross induction why Keen's statement holds. Because you can, if the Keen's condition is satisfied, you can always apply the Ross induction and do it forever and ever. And then it means that you get a smaller and smaller support interval. And so at some point you will get arbitrarily smaller support interval. But then if you go back, it means that your orbits, since they're preserved by this application, by this map, so you can be sure that all of them visited this very, very small neighborhood, arbitrary small neighborhood that you got as a support interval. So it means that they were everywhere dense at the very beginning because they finally came very close all together. And so then you can distribute it on the whole interval. So it's not a proof, huh? It's just an informal explanation why it's true. Okay, so at this point, I would like to leave the interval exchange transformations. I hope that you get a little bit familiar with them, despite the fact that they were so much studied also by such brilliant people. It still remains pretty open as a field, and there are many interesting questions, not only the ones that I mentioned to you. And so now I think I'm ready to define you the double rotations and in general, the interval translation mappings. So let me start with the more general case of interval translation mapping. Actually, I will do more or less the same things that I already showed you. So I will take an interval of a real axis and divide it into parts as I like. So on a finite number of parts. And now I will consider still the translations of these subintervals that I took as parts, but I will allow them to overlap. So I don't require anymore that I get precisely the same interval. It could be just a part of the interval, and some points are allowed to have, for example, several pre-images. It's not anymore a one-to-one map in this sense. So this object was introduced in 1994 by Bashor-Nitzan and Isaac Kornfeld. Their motivation also came from the study of some billiards, but very particular one. It's so-called billiards with spy mirrors. It means that you take a billiard and you add some kind of obstacles on the way of your ball, and these obstacles work as follows. You can go without any problem from one side and you have a reflection from another one. And it's kind of a state boundary when many countries, they do let you in, but then their citizens require a visa to enter your country. So that's more or less what happens here. Another motivation comes from the fact that just it's a very natural generalization of interval exchange transformations. And you still have a map T from the interval to itself. But now the situation changes a bit. As you see, the image does not coincide necessarily with I. So they can be classified into two groups. And it depends on the following fact. Let us say that we consider the image after the number of iterations like this. So if at some point we have a stabilization, that's exactly what happens for interval exchange at the very beginning. But even if it doesn't happen after the first step, but if at some point you get a stabilization, then we say that you have a finite type interval translation mapping. And basically it means that you have interval exchange transformation, and everything we said about its dynamics can be simply repeated for this situation. But then there exists a situation when it's not true. So such an n does not exist. And you get a kind of a counter set at the images. So it becomes smaller and smaller. And in this case, we say that our ITM belongs to infinite type. And the first example was constructed in the same paper by Bosharnitsan and Kornfeld. So, sorry. The general question is, what can we say about the orbit of infinite type ITM? But before we go deeper into this part, first we need to do the following thing. If these examples are rare, if it's hard to find infinite type ITM, then we have a kind of difficulty. Because you remember, when I was talking about interval exchange transformations, I was always referring to the fact that we have almost always this or that situation. But then if they occupy a subset of a measure 0, it means that I cannot use the Lebesgue measure anymore to describe the typical behavior of my orbit. I need to introduce a different measure for it, and then pose in a precise way the question, what can we say about the orbit behavior? So there is a conjecture that exactly this difficulty exists. So it's a conjecture by Bosharnitsan and Kornfeld that almost all ITMs are of finite type. So typically we have interval exchange transformations. This conjecture is not proved in the whole generality, and it is only known for a few subclasses of interval translation mappings. And the first subclass was described by Serge Trubetskoy and Hank Bruin in 2004, I guess, and then slightly generalized by Bruin a bit later. So they deal with the following situation when they have 3 intervals, but they know that the last one is mapped in a way that his first point is glued with the leftmost point here, and these 2 guys are taken like this. So this is their class, and for this class, the conjecture is proved. We know that almost all interval translation mappings are of finite type, of this class. So this is Bruin-Trubetskoy class. Bruin slightly generalized it in a way that he considered some abstract number of intervals, and he still did the same thing. He glued the last one to the left side and all others to the right side. So their proof uses some kind of induction, morally a bit similar to Roth induction, but much less geometrically meaningful, because you could not interpret it as a first return map to the subinterval. So very recently, in a work which is still work in progress with Mauro Artigiani, myself, we found another induction that would allow us to do the same thing as we did, as they did. So to prove the conjecture by Boshelnitsan and Kornfeld, but also to add a result on unique ergodicity and to construct some natural measure to the set of parameters that correspond to infinite case. Another important thing that Trubetskoy and Bruin did, they constructed examples of non-uniquely ergodic ITMs. This we have not repeated yet with our renormalization. So our next goal, which is now our work in progress with Mauro, is to check what can we say about weak mixing. Because for strong mixing, one can simply repeat the proof for by Katok for interval exchange transformations. So the second class for which double rotations, for which we have the proof of the conjecture by Boshelnitsan and Kornfeld, is called the double rotations. In this case, we do not live at the interval, but on the circle. We divide it into two parts, and then we consider any translations we want, for example, like this one. This class was defined first in a paper by Suzuki, Ito, and Aihara. It's around 2005. And these people also introduced some renormalization procedure, but once again, as in case of Bruin and Trubetskoy, it's not very geometrically meaningful. And in particular, it does not allow us to present it as a Markovian multidimensional fraction algorithm. Still, this renormalization was used by Henk Bruin and his student Greg Clark in 2011 to prove Boshelnitsan-Kornfeld conjecture for double rotations. And recently, with several collaborators like Mauro Artigiani, Pascal Hubert, Charles Fougeron, we constructed a new renormalization, and we proved once again the same conjecture for double rotations, but we also added a few observations, such as unique ergodicity, and which is even more important, the invariant measure. So we could state precisely what do we mean by unique ergodicity, because we said that there exists a natural measure at the parameter space, and this measure is invariant with respect to our induction, and almost every double rotation with respect to this measure, almost every double rotation is uniquely ergodic. So that's what we proved. Still, there are many open questions. In particular, if you compare these two classes, you would see that the class defined by Trubetskoy and Bruin, it gives a codimension 1 set in the set of all double rotations. So if you consider a generic double rotation, you cannot use their results. And there is a natural question about the existence of non-uniquely ergodic examples. Then you can ask a question about weak mixing. Once again, the strong mixing does not hold, you can be sure about it. And of course, there is a very challenging open question. What can we say about the general ITM on an arbitrary number of intervals? And the best thing that we have in this direction, due to the absence of renormalization, we don't have much information. We even cannot say about ergodicity, unique ergodicity, and so on. And the only smart thing we can say is the observation on the number of invariant measure, and some upper bound was proved by Jérôme Bouzy and Pascal Hubert, and it gives you the number of intervals. But it's completely not clear that this observation is accurate and efficient in a sense that you can get such a number of measures. There are absolutely no examples of non-uniquely ergodic ITMs on more than 3 intervals that do not fit in the Bruins class. So there are pretty few open questions that are easy to explain, but still it's very interesting to get any information. So welcome on board. And if you have free time, feel free to think about it. And I would like to complete it with the following plot from symbolic dynamics. Actually, interval exchange transformations that we started with, let me show you the first pictures. It's very easy object for the symbolic dynamics, because naturally any orbit can be coded by the letters. One letter corresponds to one interval, and so you can follow the trajectory of every point right in a word in your language. For example, I don't know, this is blue, red, and the yellow. And so if you take a point here, for example, it goes again to the blue, so it's blue, then blue again, and then it goes to red, and then to red again, and so on, and you get a word. And so as people typically do in symbolic dynamics, you can ask a question about the complexity of this language. So how many words of length n do you have? And apparently, for interval exchange transformations of Keen's type, there is a precise formula. So if n is the number of intervals and you have words of length d, then you will have n-1 d plus 1 as a p of d. This is a formula for complexity. And if your interval exchange transformation is not generic, if it does not satisfy the Keen's condition, you have to replace your equality by inequality, non-strict one. So you have this formula, and you know that the complexity is sublinear. Then in the case of ITMs, much less is known. In particular, it is known that you have a linear complexity for Trubetskoy-Bruin case. You do not have a very good formula, but there were some estimations for double rotations. And we know that the complexity is not more than quadratic, but there is an open question if it's indeed superlinear or it's, in reality it's still linear. And so there is completely no information for the general ITMs. And that would be also interesting to understand what we can say about the complexity of ITMs. And if we can improve it, it's quite obvious that it cannot be more than polynomial, but if we can get something better than a polynomial estimation. And I think it's better to stop here because I told you everything I wanted. And thank you very much for your attention.
Thank you very much for giving us this talk today. And let me just, sorry. I don't know if anyone has a question for our speaker.
I have a question. Yeah. Thank you, Alexandra, for the talk. Okay, so my question is for this Hubert-Bussy, that they bound the number of measures. Do they use the Kakutani-Rocklin towers? Or, no, what actually my question is, I mean, you have zero entropy here, but do you know if you have a finite rank?
It's a good question. Thank you for the question. I think so, but I guess that there is no precise proof for it. It was very barely studied from the point of view of symbolic dynamics. Indeed, the Rocklin tower is some natural tool to study them, but not much is known. But indeed, I would expect the finite rank here. I think it's not ugly enough to have infinite rank. But say nobody wrote this result. And Hubert and Bussy, they did something much more simple in its spirit to estimate the number of measures and closer to what which did in some sense.
Okay.
I have another question. So there's a general version of interval transformation that are called Lambda Expanders. Maybe you know this kind of transformation are really piecewise linear maps from the interval to the interval. And it's, well, the derivative where it is fine, it's constant and it's one slope, that it's lambda. So do you know about this kind of mappings, if there is like some theory of unique ergodicity or yes,
I'm not
invariant
sure.
measures?
To be honest, I have not heard about the Lambda Expanders by this name, but indeed there is a fine version of interval exchange transformations.
Yeah.
There is it looks very similar to what you said now. One have to write it up to be sure that it's exactly the same thing, but it looks very similar. So for affine exchange transformations, indeed, there is some theory related to it. And the main names in this direction are Jean-Christophe Yocos, Stefano Marmi, and Pierre Moussat. They studied it for a while, and they have some results on the ergodicity, but they also studied the question concerning wandering interval and this kind of properties, because once you do not preserve the length, you have to check what's going on. And it would be interesting to generalize what they did to the case of interval translation mappings also. But I think it was never done. So for interval exchange transformations, I think that it exists and some theory is quite well developed. For any other objects, I don't think so, because even for interval exchange transformations with flips, when you're allowed to change the orientation, already a final generalization was never studied.
And a second question, then in the interval exchange transformation, you can associate a translation surface with this measure on a transparent interval. But so in your generalization with these interval transformation mappings, what is the object that you get? I think actually, you said about the mirrors, but I don't know in general, is that happening in the translation?
It's a good question, and it's not obvious, because apparently what you typically would have, it's easier to define even for a more general object, which is called systems of isometries. So when you do not divide the interval, but you just consider the translations of some parts of an interval. And in this case, it is associated with so-called band complexes, an object that was widely studied in the geometry group theory, when people were interested in the action of free groups on R3s. So what you do is basically you glue some kind of a two-dimensional complex that looks like bands that are glued to some stick that you use as a support interval.
Yeah.
So it's not a surface anymore, but it's quite close to it, and you still have a foliation on it. So people used to study this thing, and for the case of interval translation mapping, there is not such an object, such an obvious dual object as translation surface. Still, when you deal with this billiards, you can consider this Katok-Zemlyakov construction as you do for classical billiards, when you reflect the whole billiard, and then you can try to glue a surface from it and so on. But it's a more delicate thing, and it's not so beautiful as a translation surface in its spirit. So I think people worked more with systems of isometries in this context than with interval translation mappings.
Yes, maybe you get a semi-flow in a branch surface or something, like gluing ribbon.
Yeah. You can define a suspension flow in this way, and you actually still what is a bit more delicate is the following thing, that when you work with interval exchange transformations, this flow has a precise geometric meaning. It's a Witch flow, and it's a cover of a Teichmüller flow in the moduli spaces of curves with one form on it. And here kind of you miss this algebraic geometry part of this plot. maybe it exists, but we don't have any results on it. And so it's much harder to understand what kind of fluid do you have. You construct it in order to prove our result, you construct it artificially, but you struggle to give a precise geometric meaning to it.
Okay, thanks.
I don't know if anyone else has an additional question.
So I have a comment. The mirror, this spy mirror situation is exactly the Mexico-United States. Actually, if you are in United States, you can cross to Mexico even without ID. I mean, like the border is like if you go like from San Diego to Tijuana, it's not even. I mean, you don't. They don't. It's just like a door that.
I understand what you mean. So on the opposite side, you need a visa, and you will be reflected easily.
Yeah, but yeah, for United States to Mexico, you don't even need ID. Like not even passport. You can just walk.
I understand well. Yeah.
So it's so you can very well call it the Mexico-United States.
It's not a rare situation. I told you that I immediately had this in mind, but also because it's the same with Russia and Georgia. You need an ID to cross the border from Russian side, but you don't need a visa. And from the other side, it's very hard to get a visa if you are Georgian to come to Russia. So it's very ridiculous, but it exists.
Well, then I think we should. Sorry.
So I mean, I have a very quick last question. So I guess in the case where you have infinite intervals, do you have like I mean, I know even for interval exchange is very hard question because I mean basically you can have anything, but there's some examples that are kind of nice, but like the Loch Ness monster and things like this. But for these ITMs, have people studied infinite cases with infinite intervals or not? Or they're...
To be honest, I never saw it, but maybe I just missed somebody's paper, but I never saw any results in this direction.
I think for interval exchange, there's very little, like just some examples. I mean, there's some results. I don't remember the authors that you can have anything. If you have infinite.
For EATs, there were some results by Pat Hooper, I guess. Not many, but he worked a bit with this situation. But I don't know anything for interval translation mappings.
Okay. Yeah. Okay, that was my last.
All right. Is there any other question for our speaker? Well, if there's not any, I think we should just thank Alexandra again for coming and giving us this very nice talk on interval exchange transformation and double rotations. And we'll just give her an applause, like virtual applause.
Thank you. Thank you very much for the invitation.
Thank you very much for coming. And I think we will meet next week.
Okay.
With, well,
yes,
have a nice day.
No se salgan.
No se salgan.
No se salgan, ¿qué onda?
No, nada para hacer el anuncio de la próxima que va a hablar Andrés, que ahorita está con nosotros. Y de hecho es una plática muy relacionada, pero como que creo que quieres dar una prueba, ¿no? De la ergodicidad única.
Pues básicamente soy como un visitante en esto de sistemas dinámicos por ahora. Por azares del destino estoy estudiando esto de justo las transformaciones de intercambio de intervalos. Y pues voy a dar pues mostrar la prueba de Kerckhoff, creo, y con algunas ideas de Marcelo Viana. No sé si bien esa es la prueba, es justo la de Beach y Mazur, pero sí hablaré de cosas que ya están escritas por mucho tiempo, o sea, nada nuevo.
Sí, pues gracias, Andrés. Sí, sí, Andrés es más como topólogo de bajas dimensiones y así, pero pues nos va a hacer el favor de contarnos más de cómo vale estas pruebas, estos resultados como de ergodicidad única. Entonces, muchas gracias.
Sí, con gusto.
Muchas
Bien.
gracias y pues esperamos. Ah, nada más para confirmar si es a las 4 la charla el próximo jueves, ¿no?
No sé si la quiera más temprano porque él está en Alemania.
Pues tal vez a las 3 para que... Sí, sí. A las 3.
Sí. Ah, bueno, está bien. Entonces también para confirmar bueno, para confirmar toda la logística.
Ah,
¿Mm?
Sí, sí, si quieres más temprano está, o a menos de que, digo, no sé qué horas sean las 3 para ti.
son las 10 de la noche.
Sí, entonces si te queda un poco más temprano, pues igual ya estaría mejor. Bueno, para ti.
Pues no sé ustedes. Pues podría ser esta hora que también igual. No sé si puedan. De 9, si son las 9 allá, ¿no? 9 a
Sí.
10. Pues estaría genial si pueden enviarlo. Sí.
Pues creo que sí, ¿no?
Sí.
Creo que a los únicos que no vi fue... pues entraron casi todos, entonces creo que sí está bien. Creo que sí está bien la hora. Pues sí, si no hay...
Pues sí, si no hay objeción, entonces nos vemos igual aquí de 9 a 10, hora de México, que serían de 4 a 5, ¿no? En Alemania.
Sí.
Sí.
Bueno.
Perfecto.
Mucho
Bueno,
gusto.
Sí, pues gracias, Andrés.
gracias.
Que estén bien.
Dale, nos vemos.
Hasta
Bye
luego.
bye.